Chemistry, we're moving on to our next lesson in the Foundations unit. This is on the subject of ionization energy. It's a topic we'll talk about almost every day for the rest of the course. So previously, we're going to start off talking about Coulomb forces. We said that similar charges repel and different charges attract each other. These are referred to as Coulomb forces. Now, the numeric formula for getting the magnitude or the amount of the Coulomb forces is given by this equation, which is K, and that's called the Coulomb constant, times the two charges, charge 1 and charge 2. Those could be a proton and a proton, or a proton and an electron, or two electrons. So that's Q1 times Q2, and it's over the distance squared. Some formulas use R instead of D for that, but it's the same thing. It's the distance between the two charges squared. And down there at the bottom, you can see the number value of Coulomb's constant. So there it is. Positive repels positive, positive attracts negative, and negative repels negative. Almost everything that happens in chemistry is a result of Coulomb forces. So I'm going to give you a number example. They would not on the AP exam ask you to work one of these. I'll ask you to work a couple in the exercises, mainly because it gives you practice with dealing with scientific notation math. Okay, so there's the formula. So there are the numbers plugged in. So the 8.99 times 10 to the 9th is Coulomb's constant. Then up at the top, you have 1.602 times 10 to the negative 19th. Then you have a negative 1.602 times 10 to the negative 19th. That's the charge on a proton and an electron. One of them is positive, the proton. One of them is negative, the electron. Down at the bottom, you have the separation between them, which is 0.71 nanometers. Now, if you go back to one of your earlier lessons, nm is nanometer. That's 10 to the minus 9th meter. So you substitute that n with 10 to the minus 9th. And then that has to be squared. So this is a little involved just doing basic math calculation on this. So what you do is first multiply all the coefficients on top and divide by the one on the bottom. So it's 8.99 times 1.602 times negative 1.602 divided by the 0.71 on the bottom, and you have to square that 0.71 on the bottom. And when you do all of that, you get the number you see there, 45.7686. Now what you have to do is deal with the exponents. So on the top you have a 9, minus 19, minus 19 again, and then down on the bottom it's a little tricky. It's negative 9 squared, and the way you deal with those exponents is you say 2 times negative 9 is negative 18. That's the principle of exponents. When you have one inside the parenthesis and one outside like that, you multiply them. So it becomes negative 18th. But remember, when you divide by a number on the bottom, that's going to be a positive number. So that negative 18 becomes positive 18. Okay, since it's on the bottom, it's minus negative 18. That's the point. So that becomes plus 18. When you add all of those together, you get negative 11. And so your answer is going to be to two significant figures. Because that's all you have in the 0.71. It's going to be 46 times 10 to the negative 11th. But that number 46 has to be a number between 1 and 10. So you move the decimal over, make it 4.6. You made the coefficient smaller, so you make the exponent bigger. So it goes from negative 11 to negative 10. That's a movement in the positive direction. That's making it bigger. Okay, so that's a lot of math involved in that, and that's maybe why I'll assign you some of these problems, is to get used to dealing with that kind of math. Lithium has an atomic number of 3. The atomic number is called the Z number, and the atomic number is the number of protons in the atom of an element. So there we see a lithium atom. You can confirm that on your periodic table. Core electrons are the electrons inside of the valence orbital. So remember, the valence orbital is the outside orbital, whatever the outside orbital for that atom happens to be. For lithium, it would be the second orbital. So core electrons would be any electrons that are in the first orbital, anything inside the valence orbital. So the core electrons are said to screen or shield the valence electrons from the pull of the protons in the nucleus. So there's lithium. There's the atom. So core electrons are all electrons inside the valence orbital. These electrons screen the valence electron from the pull of the proton. So you can see how those two electrons in the first orbital are kind of blocking the outside orbital, the valence electron in the outside in the valence orbital, from feeling the pull of those positive charges. All of them are feeling the pull, but the inside electrons are kind of blocking it. Valence electrons are the electrons in the outer orbital, so there's the valence electron in lithium. It just has one. The effective Z number, Z subscript EFF, that means Z effective, measures how much of the pull of the protons an electron feels. And it's a very simple formula. The Z effective equals the Z number, which for lithium is 3. That's how many protons it has, minus the number of core electrons. And it has 2 core electrons. So it's a simple formula. Z effective equals 3 minus 2 equals 1. So lithium has a Z effective number of 1. Although lithium has 3 protons, its valence electron feels the effective pull of only 1 proton. So that's what Z effective number is telling you. Even though lithium has 3 protons pulling on the electrons, effectively 2 of them are blocked out by those 2 core electrons. It's almost like you could cancel them out, the 2 pluses and the 2 minuses. And so the valence electron in lithium only feels the pull of 1 proton. What that means is it's not being held very tightly to the lithium atom, and therefore it can easily be pulled away from the lithium atom. So there you see I subtracted, or I canceled out, the 2 core electrons and 2 of the protons. They didn't really disappear, but that's effectively what that outside valence electron is feeling. It's just feeling the pull of 1 proton. If it's only feeling the pull of 1 proton, it's not being held very tightly into the atom, and therefore can be taken out of the atom or ionized very easily. So ionization energy is the amount of energy that is required to pull an electron from its atom. The man represents ionization energy. The ionization energy must have a greater pull on the electron than the protons do. The pull of the protons is called the binding energy. It's just binding the electron. They have more energy pulling that electron away from the lithium atom than the protons are pulling on it with, then it will leave the lithium and the lithium will become ionized. Ionization energy is also called electron binding energy. So, ionization energy increases as you go to the right on the periodic table, and it increases as you go up on the periodic table. So ionizations increase up a group, that is up a column. A column is called a group, and to the right as you go from left to right across a period or a row. That means the highest ionization energies are in the elements to the upper right-hand side of the periodic table. That would be helium, fluorine, neon, oxygen, some of the others that you see around in that area in the upper right where those arrows are pointing. Ionization energy is greatest in the upper right-hand corner of the periodic table where helium is. So you can see kind of a perspective diagram at that. And it's lowest on the opposite side of the periodic table, down in the lower left-hand side. That's where the ionization energies are the lowest. That means the elements down on the lower left-hand side, like CS, cesium, Rb, rubidium, K, potassium, can easily have their valence electrons removed from them. Whereas helium, neon, argon, fluorine in the upper right-hand corner, it's very difficult, almost impossible, to pull electrons, valence electrons, away from those elements in the upper right-hand corner. So lowest on ionization energies, highest ionization energies. Okay, now this is a trend that you could be asked on the AP exam, is to explain why the ionization energy increases either as you go from left to right across a row, a period, or from bottom up to the top in a group or column. Okay, so we're going to explain that right now. So ionization energies are lowest when an electron is furthest away from the nucleus, that is, the atom has more orbitals, or the nucleus has fewer protons. So let's take a look at those. So let's look at lithium there on the left-hand side. Lithium has a low ionization energy for its valence electron, a lower ionization energy than fluorine, because its valence electron is the same distance from the nucleus as fluorine's electron. Now confirm that. Be sure you understand why. They both have two orbitals. They're both in the second row. So they both have their electrons, their valence electrons are all the same distance. Now you might say, wait a minute, lithium only has one valence electron, and if you count, fluorine has 7. That's true, but it doesn't matter. They're the same distance away. So let me say that again then. Lithium has a lower ionization energy for its valence electron than fluorine because its valence electron is the same distance from the nucleus as fluorine's, but it has only 3 protons to attract it, while fluorine has 9 protons to attract it. And so what you want to look at here is the Z effective, and we'll do that in just a moment. But if you do the calculation, I'll do that right now. Lithium has a Z effective of 1. We did that a few slides back. Its valence electron only feels 1 proton. Whereas fluorine, it only has 2 core electrons, first orbital electrons, the same as lithium. But it has 9 protons. So its Z effective would be 9 minus 2 is 7. So all of those valence electrons, even though there's more of them, all of those valence electrons feel the pull of 7 protons. Let me say that again. Fluorine has 9 protons. It has 2 core electrons, the 2 first orbital electrons, so 9 minus 2 is 7. So fluorine has a Z effective number. Its outside electrons, valence electrons, feel a pull of 7 protons, whereas lithium's 1 valence electron only feels the pull of 1 proton. So that means it's a lot harder. Those outside electrons are feeling a greater pull, and therefore it's harder to pull the fluorine valence electrons away than it is to pull the lithium valence electron away. So Z effective for lithium is 1. Z effective for fluorine is 7. Now, let's talk about up and down. Up and down is a little more obvious, but maybe not. Bromine has a lower ionization energy for its valence electrons than fluorine because it has more orbitals. So look at the outside electrons in the bromine atom down there. Look at all the core electrons that are in between the nucleus and those outside valence electrons. There's a ton of them. They're all over the place there. So therefore, the bromine nucleus does not pull in or they have a very low pull from the nucleus of the bromine atom. Okay, so let's read this. Bromine has a lower ionization energy for its valence electrons than fluorine because it has more orbitals. So its valence electrons are farther from the nucleus. Now, if you're thinking, you're going to say, wait a minute, but bromine has a lot more protons than fluorine. So when you're going up and down a column or a group, it's the number of orbitals that determines the ionization energy. The more orbitals, the lower the ionization energy. That is, the easier it is to pull an electron away from the valence orbital. When you're going from left to right, it's the number of protons. The number of protons, the more protons, the harder it is to pull an electron away from the valence orbital. So the driving factor means the predominant or the dominant factor, going from left to right is how many protons. More protons, higher ionization energy, harder to pull the electron away. Going up and down, more orbitals means lower ionization energy because there's so many core electrons. So it's easier to pull an electron away from bromine than fluorine. So fluorine has the highest ionization energy of those elements. Of lithium, fluorine, and bromine, fluorine has the highest ionization energy. So learn that explanation. I'll have you practice it on the assignment. So each electron in an atom has its own ionization energy. These are called the first ionization energy for the first electron ionized, the second ionization for the second electron, and so forth. The valence electron of the lithium has the lowest ionization energy. It is the easiest to pull away because it is shielded from the nucleus and has a Z effective of 1. Number of protons minus number of core electrons, 3 minus 2. There it goes. The first ionization for lithium, and it's a known value, it's 520.2 kilojoules per mole. And we'll talk about what that unit of measure, kilojoules per mole. It's how much energy per mole of electrons, and we'll learn what a mole is in the next few lessons. Note that the units kilojoule per mole are a measure of energy we will discuss later. Each electron in an atom has its own ionization energy. These are called the first ionization energy for the first electron ionized, the second ionization energy for the second electron, and so forth. The second electron of lithium has a much higher ionization energy. It is not shielded. It doesn't matter which one of those two is the second one. It is not shielded from the nucleus, and it feels the pull of all three protons because there's no core electrons inside of either of those two electrons. So it's simply going to feel the pull of all three, so its Z effective is 3. So there it goes. And the second ionization energy of lithium is 7,298 kilojoules per mole. Okay, and we've already read that. I'll move on. The last electron of lithium has the highest ionization energy. It is not shielded from the nucleus, just like the last one, and feels the pull of all three protons. But in addition, it does not feel repelled by the other first orbital electron. Remember, those two electrons are going to repel each other. So they're going to kind of try to push each other out of the atom. But in this case, there's no second electron to do that. So in addition, it does not feel repelled by the other first orbital electron, which has been removed. And it also has a Z effective of 3, but it doesn't have that other electron to try to push it out. So it has the highest ionization energy. And that third ionization energy is 11,815. Okay, so that takes care of this lesson on ionization energy. As I say, it's something that we're going to be dealing with in almost every day throughout this course.